All right, let's talk about Newton's third law. So, Newton's third law tells us that for every action, there's an equal and opposite reaction. Meaning that, for instance, if I push down on the table with 10 newtons worth of force, the table is going to push back up on my hand with 10 newtons worth of force. Right? If I increase the force that my hand applies to the table to 20 newtons, well, the table reciprocates and applies a 20 newton force back upwards on my hand. Um, or if we want to take another example, let's say you got the Earth and the Moon, right? There's a gravitational force of attraction between those two. Well, the Earth is going to pull on the Moon with the same amount of force as the Moon pulls on the Earth. Now, keep in mind, these forces that we're talking about, these are two forces that are applied to two different objects, right? So if we're looking at the Earth and the Moon example, the Moon has a force exerted on it by the Earth, and the Earth has a force exerted on it by the Moon. And so these are what we call action reaction pairs. So keep in mind that there can be multiple action reaction pairs for any scenario. So let's say we've just got this pencil sitting on the table. Well, one action reaction pair could be, well, the pencil pushes down on the table pushes back up with equal force on the pencil. But there's also going to be an action reaction pair between the earth and the pencil, right? The pencil has weight. There's the force of gravity acting on the pencil. So the earth pulls on the pencil, and the pencil pulls back on the earth with equal amounts of force. All right, so in any given scenario, you can have multiple different action reaction pairs. Um, so, good example, for instance, is that one in the notes, right? How do you walk? Well, your foot pushes backwards on the earth, and the earth exerts a frictional force forward on you. You propel yourself forward. Now, let's take a look at these couple conceptual examples. So, what makes a car go forward? It's similar to the foot on the earth scenario, right? The tire exerts a force backwards on the earth exerts a frictional force forward on the tire, the car is propelled forward. Now, when we're talking about some of these examples, one that always throws people for a loop is how rockets work. Um, right? Because they think, okay, well, in space is a vacuum, there's no air. So what is the rocket pushing off of in order to propel itself? Right? Because if we think about, let's say, a swimmer, well, how does a swimmer propel himself through the water? He pushes backwards on the water, and the water pushes back on him with equal force, propelling him forward. Well, in space, there's no substance to push back on, right? So if we're looking at a rocket, well, your rocket ejects propellant, right? And it applies some force on that propellant. Well, the propellant, according to Newton's third law, pushes back on the rocket with equal amounts of force. That's how your rocket propels itself through space. If you want, go on YouTube and just Google skateboard and fire extinguisher. It's the same general idea as a rocket, right? The fire extinguisher is going to exert a force on the foam. The foam's going to exert an equal and opposite force on the um, fire extinguisher, right, which is being held by someone on a skateboard, and it's going to propel them forward. Now, the second conceptual question in the notes I really like because it gets a lot of people. So it tells us that while driving down the road, a firefly strikes the windshield of a bus and makes a quite obvious mess in front of the face of the driver. This is a clear case of Newton's third law of motion. The firefly hit the bus hits the firefly. Which of the two forces is greater, the force on the firefly or the force on the bus? So pause this for a second, think about that. All right, a lot of people are going to say that it's the firefly. And the reason they're going to say that is because, well, the firefly is completely destroyed by the bus, right? So therefore, they think that the force acting on the firefly had to have been greater. But let's take a look at it from a mathematical perspective. Now, we know that the force on the bus has to be equal to the force on the firefly. The reason we know that is because, again, these are called Newton's laws of motion. They're not Newton's polite suggestions of motion, right? So Newton's third law must remain true because, again, it is a law. Well, how are these two forces equal? Well, let's take a look at it in this way. The firefly has a real tiny mass, but it experiences a huge acceleration. Whereas the bus has a huge mass and it's going to experience a tiny acceleration. Right? The amount that the bus slows down due to hitting the firefly, it's basically immeasurable. Right? So it's because of these differences in masses and accelerations that your forces can equal out. And so those are the scenarios that they always try to trick you with, right? The same principle applies for, say, a rifle. Well, you fire a rifle. The bullet has a tiny mass and a huge acceleration. The rifle, compared to the bullet, has a huge mass and experiences a small acceleration, right? That's why the kick doesn't tear your arm off. So those forces are equal, it's just that you have that discrepancy in mass and acceleration. So you always want to avoid falling for that. And then the last conceptual example in the notes deals with Michelangelo. So Michelangelo's assistant has been assigned the task of moving a block of marble using a sled. He says to his boss, when I exert a forward force on the sled exerts an equal and opposite force backward, so how can I ever start it moving? No matter how hard I pull, the backward reaction force always equals my forward force, so the net force must be zero. I'll never be able to move this load. Alright, so the thing with Michelangelo's assistant is he's assuming that him and the sled exist in a closed system, meaning that they're the only two objects in existence. If that were true, then yes, he wouldn't move. But again, there's always the possibility of having multiple action reaction pairs. So in this case, there's not just that action reaction pair between Michelangelo or the assistant and the sled, there's also the action reaction pair between him and the ground. Right? He's exerting a force backwards on the ground is exerting a frictional force forward on him. So in that case, right, he's just ignoring the fact that the world is more complex than just the interaction between two objects. Right, there's another object he's ignoring. He's not taking into account. So that's Newton's third law. I'll put up some concept questions here in a bit. I've also uploaded some old free response problems that you should take care of. There's keys up there. Because really, when we're dealing with forces, it's just like any other thing in life. The more you practice it, the more you apply forces into different scenarios, the easier it becomes. So make sure you're taking care of that. And yeah, see you in the live sessions.